Now, as long as we're on the topic of the law of conservation of angular momentum, I want you to picture this. There's a rotating bar stool, and you take a seat on it. You take your feet off the ground and rest them on the footrest, and then you extend both of your arms as far as they can go, and in each hand you hold some little dumbbell. And then maybe a classmate comes from behind, grabs you by the shoulders, and gives you a little whirl and sends you spinning with some initial angular velocity omega naught. And then you pull inward with your arms, and next thing you know, here you are sitting on that bar stool with your feet resting on the feet rest, and now your arms are pulled in and you've got these dumbbells close to the central axis near the middle of your body. What would happen? I believe the angular velocity would be quite a bit greater in this case. Now let's just make up some numerical values. Let's say that the initial rotational inertia, and here's some compound system. I don't know the formula for the rotational inertia of a person about this axis. Okay, but I know this much. When the weights are held far away, that makes the rotational inertia larger. And when the weights are pulled in close, that makes the rotational inertia less. So maybe the initial rotational inertia is 8 kilogram meter squared, and after the weights are pulled in, it drops down to 5 kilogram meter squared. Okay, and let's say the initial angular speed is, how about 6 radians per second. That's about 1 revolution per second, isn't it? Okay, that's believable. And maybe the final angular speed goes up to, well, let's figure it out, right? That's not a question because this represents an isolated system. As long as your feet are up off of the ground, there's nothing to exert an external torque on this system, so angular momentum has to be conserved. So the initial angular momentum has to equal the final angular momentum. Well, that just means I naught times omega naught has to equal I final times omega final. So the final angular momentum has to be equal to the initial angular momentum multiplied by this ratio of rotational inertia. So the final angular speed, or did I misspeak? Did I say final? The final angular momentum and the initial angular momentum are equal. So the final angular speed is equal to the initial angular speed times a ratio of rotational inertia. Okay, final angular speed numerically then is 6 radians per second times this ratio 8 kilogram meter squared divided by 5 kilogram meter squared. Okay, so this means our final angular speed is 48/5. All these units cancel out, so radians per second are the final units, and 48 divided by 5 is 9.6 radians per second. Okay, easy enough. So the bottom line is you speed up. Your angular momentum doesn't change, but you rotate faster. And I believe I have a video where I demonstrate myself sitting on a bar stool and doing something of this sort. So if you haven't watched that video yet, maybe you want to hit pause right now and have a look. Okay, so we agree you spin faster as you pull the weights in close to your body. This is the same thing that an ice skater does, right? I don't watch a whole lot of ice skating, but when the Winter Olympics roll around, I tune in every once in a while, and it seems to be a common maneuver for ice skaters to pull their arms in, and they definitely spin faster and faster as their mass comes closer to the axis of rotation. Let's investigate the energy. The initial kinetic energy is all rotational, so it's equal to 1/2 I naught omega naught squared. This would be 1/2 times 8 times 6 squared. And the final kinetic energy is also strictly rotational, 1/2 I omega squared. So this is 1/2 times 5 times 9.6 squared. Are these going to come out to be the same value? Let's see. 1/2 times 8 times 6 squared. So this comes out to 144 joules. Okay. Do we make a mistake? This comes out to 230.4 joules. Is that possible? Can final kinetic energy be greater than the initial kinetic energy? In this case, yes. If you think about it, to pull the weights in, your body has to do work. And based on the work kinetic energy theorem, work equals a change in kinetic energy. So the kinetic energy goes up because of the work you had to do to engage the pectoral muscles and maybe the bicep muscles and whatever other muscles of your upper body had to do work in order to pull these weights inward. You can try this yourself at home. If you happen to have rotating bar stools in your house, then grab the heaviest objects you can find. I would suggest you start slowly and work your way up. So begin with a pretty modest initial angular speed and see what happens when you pull the weights in close to your body.